Today we continue our discussion of derivatives as functions. If y equals f of x equals an example function here, x squared plus 3x, the derivative can be written in a variety of ways. One of them is f prime. We're familiar with that. Y prime, since y is f of x, that's a fairly obvious notation. Dy dx, we haven't written this before, but this is related to the delta y over delta x notation for slope, and it's called Leibniz notation. Df dx, which since y is f of x is really this same sort of notation. The prime says take the derivative of x squared plus 3x, which is what we're supposed to be doing. Here's Leibniz notation, take the derivative with respect to x of what's in here. And this does not exhaust all the possibilities. Now let's look at specific functions, in particular power functions. So f of x is x cubed, and we're going to calculate f prime of x using our standard definition. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h, which becomes 4x cubed, x plus h cubed minus x cubed over h. Now what we do is expand x plus h cubed. This is the formula for the cube of a binomial. The next thing we're going to do is subtract off the x cubed. We're going to get a term that looks like this on the top. And what you notice is there's a common factor of h, which we can factor out. And we get this h over h, which we are always looking for when we do these calculations, because that's going to be 1. And then a term we can deal with. So we're going to get a 1 from this, 3x squared. That's going to be a 0, and that's going to be a 0. So we end up with 1 times 3x squared, or 3x squared, which is the derivative of x cubed. Now let's take a look at some functions we know derivatives of. F of x equals ax plus b is the equation of a line. And remember, the line has a constant slope, and the constant slope is a, so the derivative of ax plus b is a. F of x equals a constant is the horizontal line. It has a slope of 0. Now, we've already seen that the derivative of x squared is 2x, and we've just shown that the derivative of x cubed is 3x squared. Now, let me add another special case to this. The derivative of x, which is x to the 1, is actually given to us by this, where a is 1, and the derivative of x is thus 1. X is x to the 1. 1 can be written as 1x to the 0. X squared, 2x. X cubed, 3x squared. X to the first, 1x to the 0. So we've got coefficients coming from exponents. What about exponents? X squared, x to the first, x cubed, x squared, x to the first, x to the 0. So what happens is the derivative of x to this power, the power pops down and becomes the coefficient, and the power of the derivative drops by 1. If n is a positive integer, the derivative of x to the n is nx to the n minus 1. So for example, the derivative of x to the 8th is going to be 8 from here, x to the 7, where 7 is 8 minus 1. Now let's look at some other rules that are going to be useful for us calculating derivatives. One of them is, what's the derivative of a sum? Now, if we just write down the definition of the derivative of f plus g is f of x plus h plus g of x plus h minus f of x plus g of x over h. We can split this into f and g parts. And when we do, what we end up seeing is this is the definition of the derivative for f, and this is the definition of the derivative for g, and there's a plus. So what we have is f prime of x plus g prime of x, which says the derivative of a sum is the sum of the derivatives. It turns out the same thing is true for differences, and we have the derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. We could do the same sort of calculation for a constant times a function, and what turns out to be true is the derivative of a constant times the function is that constant times the derivative of the function. One warning, things are not nearly as simple for products of functions or quotients of functions. These we're not covering at this point because they're much more complicated. Okay, let's do an example, and what we're going to do is we're going to differentiate a polynomial, which we now know how to do. So we're going to differentiate the polynomial, and then we're going to find the equation, the tangent line to the graph, when x equals 1. So first step, calculate the derivative. Y prime is x cubed plus 3x squared minus 5 prime. And now remember that the derivative of the sum is the sum of derivatives, and the derivative of a difference is the difference of the derivatives. So we can just break this up as the derivative of x cubed plus the derivative of 3x squared minus the derivative of 5. Now, a lot of these things we know. The derivative of x cubed by the power rule is going to be 3x to the 3 minus 1, or 3x squared. This is a constant times a function, so the constant just factors out, and it's 3 times the derivative of x squared, and the derivative of a constant is 0. And now we want to differentiate x squared, and we've already done that before. We know that's going to be 2x to the first, or 2x. So we're going to get 3x squared plus 3 times 2x plus 0, and 3 times 2x is 6x. So that's the derivative of y. Now we want to find our tangent line, and the slope of the tangent line is the value of the derivative at the place we're interested in, which is x equals 1. So what you do is you plug x equals 1 into the derivative, which is 3x squared plus 6x, so we get 3 times 1, which is 1 squared, plus 6 times 1, which is 6x, and we get 9. So that is the slope of our tangent line. Now all we need is a point. Well, we know the x-coordinate, but we need the y-coordinate for the point of tangency, and that's going to come from the function value. Y of 1 is 1 cubed plus 3 times 1 squared minus 5, and you do the algebra and you get minus 1. So the point of tangency is 1 minus 1. We plug into point slope. Y minus y naught is mx minus x naught. And since y naught is minus 1, we have 1 minus minus 1, or 1 plus 1. And m is 9. We calculated that. It's the slope. X minus 1, because it's happening at x equals 1. And that's the equation of the tangent line. Now what we want to talk about is the second derivative. And the second derivative of a function f of x is the derivative of the first derivative. F double prime of x is the prime of f prime of x. And that's in fact exactly how we're going to calculate it. Now notationally, if we have y equals f of x equals x cubed plus 3x plus 5, the notation for the second derivative is f double prime, y double prime. Here's the function with the double prime. And then the Leibniz notation is d squared y dx squared, which is the second derivative of y. Same idea with f. And here's take the second derivative of this object. Now let's actually do that. The second derivative of x cubed plus 3x plus 5 is going to be the derivative of the first derivative. And the derivative of x cubed is 3x squared. The derivative of 3x is 3 times 1, or 3. The derivative of 5 is 0. And that's the first derivative here, but now we have to take the derivative again. The derivative of 3x squared is 3 times 2x, and 3 times 2x is 6x. The derivative of 3 is 0, so the whole thing is 6x. Now let's look at the relationship between the graphs of f, f prime, and f double prime. In this particular case, we're told that the graphs A, B, and C represents the graphs of f, f prime, and f double prime, and we're supposed to identify which graph corresponds with which function. So we'll use the notation here that graph A is the graph of the function a of x, and it's the same idea with B and C. The key idea we'll use for identification is that a function has a horizontal tangent exactly where its derivative is 0. So if we see a function with a horizontal tangent, its derivative will have to be 0. If something is the derivative of an object, when that thing is 0, the thing it's the derivative of will have to have a horizontal tangent. Okay, so we look at this horizontal tangent on graph A, and what we can see is that neither B nor C is 0 there. So neither B nor C can be A prime. So A must be F double prime, because F double prime is the only function for whom the derivative is not graphed. Now what we do is we look at the places where A is 0. So whatever it's the derivative of must have horizontal tangents there, and we see that C does, and B does not. That means that B cannot have A as its derivative, so C must have A as its derivative, and that means that C is F prime because F prime has F double prime as its derivative. We can confirm this by looking at the relationship between A and C. What we can see is that when C is increasing, A is positive. When C is decreasing, A is negative, and that's the relationship that we need between a function and its derivative. If we look at the relationship between C and B, we see exactly that same relationship. Horizontal tangents in B where C is 0, and where C is negative, B is decreasing. Where C is positive, B is increasing. Okay, and that means that B has C as its derivative, and that means that B is f of x, C is f prime, and A is f double prime. Now let's talk about distance, velocity, and acceleration. We've seen that if s of t gives the position of an object on the x-axis relative to the origin, the derivative of that function is the velocity of the object. And here we're going to assume that s is measured in meters and t is measured in seconds. If you write v of t is ds dt, the units become clear. ds dt is meters over seconds, which gives us meters per second. Now, what about the derivative of v of t, which is the second derivative of s of t? We have s double prime of t is dv dt, and now using that notation, v is meters per second, t is seconds, and if you work that out, that's meters per second, which is sometimes written as meters per second squared. Those are the units of acceleration. In fact, s double prime equals v prime equals a of t is the acceleration. So the acceleration is the first derivative of velocity, the second derivative of position. So for example, an object is launched upwards with an initial velocity of 40 meters per second. Until it hits the ground, its position is given by s of t equals minus 4.9 t squared plus 40t meters. Find v of t and a of t. So to find v of t, we take the derivative of s of t, which is the derivative of minus 4.9 t squared plus 40t. Now the derivative of minus 4.9 t squared is minus 4.9 times the derivative of t squared, which is 2t. The derivative of 40t is 40. So we end up with minus 9.8 t plus 40 meters per second for the velocity. The acceleration will be the second derivative of position, which is the first derivative of velocity, which is the derivative of minus 9.8 t plus 40. And the derivative of minus 9.8 t is minus 9.8 times the derivative of t, and the derivative of t is 1. Derivative of 40 is 0, so we finally end up with minus 9.8 meters per second squared as the acceleration. If we graph the position, velocity, and acceleration together, we see that the position function has a horizontal tangent. And the velocity, which is its derivative, is 0 there. The velocity is a line with negative slope, which means the acceleration, which is its derivative, should be that constant negative slope.